so सबको मेरी बात आ रही है? Let us start. चलें ठीक है. Okay जी, so last time we started with the chapter number 1, semiconductor diodes, and I have made slight changes in the slides. This is the slide that demonstrates the required textbook. This is our front cover and brief contents of the textbook that we are following. Electronic Devices and Circuit Theory, 11th edition by Robert L. Boylston. Okay, then is the brief contents. In the brief contents, we will start with chapter number 1. We have already started with chapter number 1. Then for diode applications, we will turn to chapter number 2. Then in chapter number 3, we will do bipolar junction transistors. In 4, the biasing and AC analysis, and after this, we have the field effect transistors and so on. Right, last time we finished up till relative mobility. So last time there was a question from one student that what is the formula for relative mobility? वो स्टूडेंट अभी बैठे हुए हैं?
Yes, sir.
Okay, so in the next slide, I will show the formula for relative mobility. So in this slide, we see the formula for relative mobility. And the explanation is that when an electric field E is applied across a piece of material, the electron responds by moving with an average velocity called the drift velocity Vd. Then electron mobility mu is defined as Vd is equal to mu times E, where E is the magnitude of electric field applied, Vd is the magnitude of electron drift velocity, and mu is the required electron mobility. And the electron mobility is always specified in units of centimeter square plus over V over volt second dot second. Then we did the energy levels, and in today's lecture we will extend the concept. We will extend our learning of energy levels and introduce the Fermi levels, inshallah. So let us start with article number 1.5. Article number 1.5 is the N-type and P-type materials. Because silicon is the material used most frequently as the base material in construction of solid-state electronic devices, the discussion to follow deals mainly with silicon semiconductors. So this is just a declination start. Then we have a definition of doping. What is doping? Doping in semiconductor production, doping is the intentional introduction of impurities into an intrinsic semiconductor for the purpose of modifying its electrical, optical, and structural properties. So doping is in fact a procedure, and in this procedure, the impurities are purposely introduced, the impurities are purposely injected, or the impurities are purposely added into an intrinsic, the 100% or the nearly 100% pure semiconductor, for the sole purpose of changing either its electrical property, its optical property, or the structural properties. Okay? So a semiconductor material that has been subjected to the doping is called extrinsic material. So when the pure semiconductor is added with impurities, it does not remain pure any longer, and it is called, as we all know, an extrinsic material. So the N-type and the P-type will be extrinsic materials, whereas the base on which doping is done is intrinsic. Right. Now we have the N-type material. An N-type material is created by introducing impurity elements that have 5 valence shells that are normally called pentavalent atoms. For example, antimony, for example, arsenic, and for example, phosphorus. Each is a member of a subset group of elements in the 5th period, or in the 5th group of the periodic table. They are given the group number 5 because they have 5 electrons in the outermost shell. When elements of the 5th group, they are added as impurities into silicon or into intrinsic silicon, what we get is an N-type material. So in this diagram shown, figure 1.7, we see there are silicon atoms that are surrounding us an antimony atom. The antimony atom has 5 electrons out in the outermost shell. Out of these 5 electrons, 4 electrons make the covalent bond with adjacent silicon atoms, whereas one electron belonging to the antimony atom remains vacant, or it does not form any covalent bond. And this we say is that here we have an electron, that it is available for conduction. However, after the covalent bonding, we must not forget that even we have one extra electron, we have one electron that is available for conduction. Even then, the polarity on the substrate is 0. That is, it is neutrally charged. That is, the number of electrons and the number of protons are equal. Therefore, there is no charge on this extrinsic material. We have doped it, and we also have one freely available electron. But if we count the number of electrons and we count the number of protons, they will be equal, and hence we can say that this extrinsic material is neutral. So this was the production technique of N-type material. Now we come to the production technique of P-type material.
Sir, can you please explain the how it is electrically neutral again?
Okay, so when we added when we added when we added the antimoney atom was neutral itself. It was neutral if we count the electrons in antimoney, and if we count the protons in antimoney atom, both are equal. So this means we are introducing a neutral antimoney atom in the intrinsic silicon. Now let us discuss the intrinsic silicon. The number of atoms, the number of electrons in the intrinsic silicon material is equal to the number of protons in the same intrinsic material. So this means that the intrinsic material is also neutral. The antimony, the impurity atom is neutral, and the intrinsic material also neutral. So when we add them, the antimony will create covalent bonds, but the number of all electrons, it will be equal to the number of all protons. Hence, there is no charge. It is neither negative nor is it positive. It is simple neutral in electrical charge. But we have, by the addition of antimony, we have one available electron which did not combine, which did not create covalent bonding with adjacent silicon atoms. It is available for conduction. This gives the creation of N-type material. Then comes the creation of P-type material. A P-type material is formed by doping pure germanium or silicon crystal with impurity atoms having 3 valence electrons. This is the only technique to produce p-type material, that we add atoms of atoms having 3 valence electrons. We add atoms that are called trivalent atoms into pure silicon or germanium, and what we get is p-type material. These trivalent atoms can be atoms from boron, gallium, and indium. All of these elements have 3 electrons in the valence shell. Right. Now in this diagram, what we see is that we see silicon atoms that are surrounding one boron atom, boron being the trivalent atom. Boron has 3 electrons in the outermost shell. These 3 electrons, they create covalent bonding with adjacent silicon atoms. However, there is one vacancy of electron, and this vacancy of electron is here due to the absence of the 4th electron, and this creates a vacancy, and this electron and this place creates a vacancy, and one electron can come and reside over here. But even then, even with this vacancy, the charge on this substrate is neutral, and it is called an acceptor atom. This structure is called the acceptor atom because we have a vacancy. We have enough space to adjust one electron in the covalent bond. So at this moment, without the additional electron, without the completion of covalent bond. It is neutral, and when one electron resides in the available space, it will become a negative ion. Hence, this system is called the acceptor atom because it is ready to accept one electron. The n-type material, in the n-type material, we saw one extra electron. This electron is ready to be donated. It is available for donation. Hence, it is called the donor. Hence, it is called the donor atom. Now, with this concept, we come to what is donor energy level. So I would like all my students to pay attention that a discrete energy level appears in the forbidden band with energy gaps significantly less than that of intrinsic material. Those free electrons, due to the added impurities, sit at this energy level and have less difficulty absorbing a sufficient measure of thermal energy to move into the conduction band at room temperature. So please everybody listen, that this is quite important to understand what is happening over here. Let us take the case of n-type material. In the n-type material, we have antimony atom which creates 4 covalent bond with silicon atom, and there is 1/5 electron available. Due to the availability of the electron, this is called the donor atom or the donor electron. Now in figure 1.8, we see the energy band diagram for doped, for extrinsic material, and for undoped or extrinsic material. Figure 1.6 shows the energy diagram for intrinsic material. Intrinsic material, the energy gap is large because there is no available electron. So we have to give a much larger energy for the electron to break its covalent bond and enter into the conduction band. And this was for pure germanium, it was 1.67 electron volt, and for silicon it was 1.1 electron volt, and for gallium arsenide it was 1.43 electron volt. Now after doping, what happens is that the band gap, the energy gap becomes less. The energy gap becomes less. How does it become less? That the free electron, due to the added impurity, they reside at the energy level and have less difficulty absorbing a sufficient measure of thermal energy. This electron will not sit in the valence shell, neither will it sit in the conduction shell. It will sit in a place in between, which is normally called the forbidden band. Yes, the available electron, it will not sit in the valence shell, it will not sit in the conduction shell. In fact, it will sit on the forbidden band. One electron normally in the Bohr's model, electrons, they don't reside in forbidden band. They reside in specific shells. The outermost shell is the valence shell, and the shell after the valence shell is the conduction shell. Normally, what we have learned in the past is that electrons, they can only circulate the nucleus in predefined shells. But here, due to the availability of electron, due to the electron that did not create covalent bond, this electron will have a special characteristic. And the special characteristic is that this electron will circulate in a shell which is called the forbidden band. And this shell will be very close to the conduction band. So we just provide a very small amount of energy, and this electron moves into the conduction band at room temperature. This is the donor energy level, and in a later few slides we will discuss Fermi levels that discuss or formalize the same article. So any question up till here?
Sir, there is no covalent bond between boron and fourth silicon.
दोबारा बोलें, क्या पूछा सवाल आपने?
जब बोरॉन सिलिकॉन के साथ कोवलेंट बॉन्ड बनाता है तो वो सिलिकॉन बनाता है.
अच्छा. So this is the case of boron. In the center we have boron. Boron has 3 electrons in the valence shell, and then we see silicon atoms that are circulating or that have surrounded the boron. 3 covalent bond exist due to boron, जिनको मैं show कर रहा हूँ. These are the 3 covalent bond due to the boron, but one covalent bond is incomplete. So in boron or in p-type material, there are only 3 covalent bonds, and one covalent bond is incomplete. This makes it the acceptor atom because it is ready to accept one electron and complete its outermost octave. Now we come to the concept of electron versus hole flow. The conventional direction of current is that current is the motion of positive charges. The conventional definition of current is that current is the motion of electrical charges per time. However, we know that in fact there is no such thing as positive charging flow. Physically, we have electrons that are flowing from negative potential to positive potential. So actual we have electron flow, but traditionally we say that we follow the tradition and assume that the flow of charge is due to the positive charge. The flow of current is due to the positive charge. This only introduces the change in direction. Otherwise, all of the magnitude will remain the same. So in this diagram, we see that as electron they move, when the electron moves, it leaves behind a hole. When the electron jumps from one position to another position, it leaves behind a hole. So an electron will jump from one place to another hole, and where it jumps from will be a hole. Now is the concept of majority and minority carriers. In an n-type material, electron is called majority carrier and hole is the minority carrier. If we have one n-type material, in the n-type material, the electron is called the majority carriers because the n-type material has excess of electrons, of available electrons. So in the n-type material, the electron is the majority carrier, and the holes are in very small amount, and they are called minority carriers. Whereas in a p-type materials, the whole is the majority. Therefore, the whole is called the majority carrier, and the electron is the minority. Electrons are in few number, therefore they are called the minority. So in this diagram, figure number 11, figure number 1.11, we see two cases. First case for n-type material, the electrons are in majority, and we have the holes, the vacancy of electron, they are in minority. And in p-type material, we have the holes in majority, whereas electrons in minority. Very few number of electrons. ये जो मेजॉरिटी कैरियर्स हैं और मिनॉरिटी कैरियर्स हैं, इनको आपने बड़े अच्छी तरीके से समझना है, बिकॉज वी विल यूज देम ड्यूरिंग फॉरवर्ड बाइसिंग एंड रिवर्स बाइसिंग कंडीशंस. सो दोबारा सुन लें कि इन एन टाइप मटेरियल the electrons are in majority, hence they are called majority carrier, and the holes, they are not absolutely zero. There is a finite number of minority, there is a finite number of holes in n-type material. However, this is a very few amount, therefore they are called minority carrier in n-type material. However, in p-type material, the holes become in excess, they become majority carriers, and electrons, they are not eliminated, they are present in a very few amount, and they are called majority carriers.
But how can we say a whole a carrier?
We say a hole is a carrier because when one electron comes and sits in a hole, this hole will now move to the location where the electron came from. So electron is a carrier also. So a hole is a carrier also, because electron moves from one place to another place. When the electron moves from one place to another place, it fills in the hole, and where it came from is the second location of the hole. So we say that the hole is the positive carrier and the electron is the negative charge carrier. Okay, now we come to a little bit in discussion with the physics of energy band gaps. We will discuss what is Fermi level. First, let us discuss the definition of Fermi. Fermi is the definition of Fermi. Fermi is a unit of length equal to 10 to the power minus 15 meter, which is also called 1 femtometer, used in nuclear physics mostly. It is similar to the diameter of a proton. This is Fermi. This is the definition of Fermi. Fermi was no person, it was no no scientist or anything. It is a, maybe it is a scientist, but it is a unit of length, and the unit of length is 10 to the power minus 15 meter, which is similar to the diameter of one proton. This is the definition of Fermi. Now we come to Fermi levels. So I would like all of the students to pay extra attention. Fermi level is the highest energy state occupied by electrons in material. at absolute zero temperature. Fermi level is the highest energy state occupied by electrons in a material at absolute zero temperature. As the temperature is increased, electrons start to exist in higher energy states too. So let us look at the first diagram. That here we see the valence shell or the valence band, and here is the conduction band. And the Fermi level is over here, this yellow colored. This is the location of Fermi level. At 0 Kelvin or at absolute zero temperature, 0 Kelvin, Fermi level is the maximum state that electrons can occupy. At 0 Kelvin, where can the electrons in the valence shell excite? That will be the Fermi level. This will be variable from elements to elements. As we increase the temperature, the electrons, they absorb energy and then they jump from valence shell to conduction shell. So as we increase the temperature, the electron, only then they can start residing in conduction cells. So what is Fermi level? Fermi level is that we give absolute zero temperature to one atom. The atom cannot no longer does not absorb any energy. The electron, since they cannot absorb any energy, they cannot jump into conduction band. So what is the maximum energy state that they can occupy? That will be the Fermi level, and it is variable from element to element. Then second case is, then when we start providing temperature, when we start providing energy to electrons in the valence shell, these electrons, they absorb the energy and then they start coming into conduction shells to such an extent that at very high temperatures, these electrons, they can reach the conduction band and contribute to electrical current. So in the third diagram, we see that at high temperatures, the electrons, what they can do is, they can now reside in a specific or in a large density in the conduction band and contribute to electrical current flow. This was the physical definition of Fermi level. Fermi level क्या होता है कि जी वो लेवल, वो एनर्जी स्टेट जहां पे इलेक्ट्रॉन्स आ सकते हो एट जीरो टेम्परेचर, जिधर आप कोई एनर्जी नहीं दे रहे, वो मैक्सिमम हाइट जो आपके, वो मैक्सिमम लेंथ या वो मैक्सिमम एनर्जी स्टेट जो इलेक्ट्रॉन जहां पे रिजाइड कर सकते हैं, वो आपका फर्मी लेवल बन जाता है। और ये हर एलिमेंट का अपना अपना फर्मी लेवल होता है। नाउ सो फर्मी लेवल
जीरो केल्विन तक,
जी जी
सर भी 0 केल्विन तक हम पहुंचे नहीं तो फर्मी लेवल तक कैसे पहुंच गए?
ये क्या सवाल हुआ?
सर अभी 0 केल्विन टेम्परेचर अचीव नहीं ना होगा।
दोबारा बोलें, क्या कह रहे हैं?
सर अभी 0 केल्विन तो अचीव ही नहीं हुआ।
वो कैसे अचीव होगा?
सर विद वेरी लो टेम्परेचर, और वो हमने दिए नहीं अभी।
देखिए 0 केल्विन कैसे आपको अचीव होगा? वी एलिमिनेट ऑल एनर्जीज, उसको 0 केल्विन की एनवायरनमेंट पे रख दें। फॉर एग्जांपल आप अपने मटेरियल को एक ऐसे इतने सर्द एनवायरनमेंट पे रखें जहां पे 0 केल्विन मेंटेन्ड है, at that time the maximum range the maximum energy where our electrons can sit, that will be the Fermi level. ठीक है?
Sir, can we say there is no free carrier at Fermi level?
There is no what? There is no what?
There is no free carrier at Fermi level.
No, there is carriers. Carriers are available, but I'm saying that at 0 Kelvin, what is the maximum energy state where the electrons can reside, and that is variable for each element. और उस लिमिट को आप बोलते हैं फर्मी लेवल. उस लिमिट को आप बोलेंगे फर्मी लेवल. फॉर सिलिकॉन इट विल बी डिफरेंट, फॉर जर्मेनियम इट विल बी डिफरेंट, फॉर आर्सेनाइड इट विल बी डिफरेंट. ठीक है? तो जब आप टेम्परेचर को 0 केल्विन कर देंगे, एट दैट टाइम इलेक्ट्रॉन्स कंडक्शन बैंड में आ ही नहीं सकते. क्यों नहीं आ सकते? क्योंकि कंडक्शन बैंड में आने के लिए उनको एनर्जी चाहिए. एनर्जी आप उनको दे ही नहीं रहे, तो वो कहाँ तक रहेंगे? वो सिर्फ अपने वैलेंस शेल तक ही रहेंगे. लेकिन इस वैलेंस शेल की भी आगे कुछ हदूद हैं, कुछ लिमिट्स हैं, और द मैक्सिमम लिमिट इज कॉल्ड द फर्मी लेवल. कुछ इलेक्ट्रॉन्स होंगे जो फर्मी लेवल तक पहुंचेंगे नहीं, लेकिन कुछ होंगे जो अपने बिल्कुल पूरे फर्मी लेवल पर रहते होंगे, एंड दैट इज कॉल्ड द मैक्सिमम लिमिट ऑफ फर्मी लेवल. और इसको फिर आप कंडक्शन बैंड में कैसे लेके जाएंगे? इनको हम ऐसे लेके जाएंगे कि आप इनका टेम्परेचर इंक्रीज करेंगे. वी विल स्टार्ट गिविंग इलेक्ट्रॉन्स एनर्जी. वो इलेक्ट्रॉन जो अभी तक वैलेंस बैंड पे पड़े हुए थे, उनको आप एनर्जी देंगे, सो दैट दे अब्सॉर्ब एनर्जी, दे कम आउट ऑफ द फर्मी लेवल. और हाई टेम्परेचर्स में वो कंडक्शन बैंड में आके बैठना शुरू हो जाएंगे. कंडक्शन बैंड में जब वो आके बैठना शुरू हो जाएंगे, ओनली देन वी कैन गेट करंट, इलेक्ट्रिक करंट. Now,
I was
Is
actually
it the
asking if at Fermi level we apply external field
जी
if we conduct electricity.
जरा बोलें, ऊंचा बोलें, ऊंचा बोलें. मुझे आपकी आवाज
Sir,
नहीं
I
आ
was
रही.
asking at Fermi level. Sir, I text you.
जी, at Fermi level what will happen? नहीं, टेक्स्ट ना करें, आप सिर्फ बात करें, जरा ऊंचा बात करें, सो दैट एवरीबॉडी शुड लिसन. वो टेक्स्ट तो सिर्फ मैं पढ़ सकूंगा, सब सुने सवाल.
सर अगर फर्मी लेवल पर हम एक्सटर्नल इलेक्ट्रिक फील्ड अप्लाई करते हैं तो फिर तो वो कंडक्ट नहीं ना करेगा कुछ भी.
फर्मी लेवल पे आप फर्मी लेवल पे आप रिजाइड करते हैं.
एक्सटर्नल इलेक्ट्रिक फील्ड अगर अप्लाई करें उस सेमीकंडक्टर पे,
नहीं, लेकिन मेरी बात सुने, ये जो आपकी एक्सटर्नल इलेक्ट्रिक, ये जो आपकी एक्सटर्नल इलेक्ट्रिक फील्ड है, क्या आपकी एक्सटर्नल इलेक्ट्रिक फील्ड इस काबिल होती है कि इलेक्ट्रॉन्स जो कि वैलेंस शेल में हैं उनको खींच ले? आई थिंक दैट the electrical field will attract electrons that are available in the conduction band. इस बात का जवाब दें मुझे। वो इलेक्ट्रॉन्स जो कि वैलेंस शेल में हैं, वो इलेक्ट्रॉन जो वैलेंस शेल में हैं, दे आर ऑलरेडी too much attracted toward their own nucleus. ठीक है? So external field will not influence them. But when the same electron absorbs energy and jumps into the conduction band, and once it is in the conduction band, it becomes out of the influence of its nucleus. Now, if it is given external electric field, it will be attracted to the external electric field. समझ में आई बात?
यस सर।
ठीक है। So अब हमारे हैं फर्मी लेवल्स ऑफ अब हमारे इन फर्मी लेवल्स ऑफ एन टाइप मटेरियल. This is quite interesting to note that the addition of pentavalent impurity creates large number of free electrons in the conduction band. The addition of pentavalent impurity creates large number of free electrons in the conduction band. ठीक है? At room temperature, the number of electrons in the conduction band is greater than the number of holes in the valence band. Hence, probability of occupation of energy levels by the electron in the conduction band is greater than the probability of occupation of energy levels by the holes. This in the valence band. This probability occupation of energy level is represented in terms of Fermi level. तो जनाब यहाँ पे इन एन टाइप मटेरियल में फर्मी लेवल आपका नॉर्मल दरमियान से हट के कंडक्शन बैंड की जानिब चला जाएगा. इट विल बी शिफ्टेड. द फर्मी लेवल विल बी शिफ्टेड. इसका क्या मतलब है? इसका मतलब ये है कि इसका मतलब सब गौर से सुन लें कि इसका मतलब ये है कि एन टाइप मटेरियल में इलेक्ट्रॉन्स वैलेंस शेल के पास नहीं होते. दे आर नाउ नियर EF, द एनर्जी ऑफ द फर्मी लेवल. इस फर्मी लेवल के पास आपके इलेक्ट्रॉन्स आ जाएंगे और उनको अब बहुत थोड़ी सी एनर्जी चाहिए. दे नीड अ वेरी स्मॉल अमाउंट ऑफ एनर्जी टू जंप इनटू कंडक्शन बैंड. ये दोबारा सुन लें कि व्हेन वी ऐड pentavalent impurity, we have large number of free electrons in the conduction band. At room temperature, the number of उसी वजह क्या है? At room temperature, the number of electrons in the conduction band is greater than the number of holes in the valence band. Hence, the probability of occupation of energy levels by the electrons in the conduction band is greater than the probability of occupation of energy levels by the holes in the valence band. This probability of occupation of energy levels is represented in terms of in terms of Fermi level. Therefore, the Fermi level in n-type material lies very close to or close to the conduction band. आपके पास we have created n-type material, we have free electrons, they are now in the conduction band, and now as conduction band has as Fermi level as the Fermi level is now very close to the conduction band, though, so it needs very small amount of energy The Fermi level of n-type semiconductor is given by this formula, where इन सब की ये जो वेरिएबल्स के डेफिनेशन है, where EF is the Fermi level, EC is the conduction band, KP is the Boltzmann constant, T is the absolute temperature, and C is the effectively density of state in conduction band. ये conduction of state अभी हमने करना है अगली स्लाइड में. And ND is the concentration of donor atoms. Concentration का मतलब ये है कि the quantity of donor atoms available. How comes the Fermi level of p-type materials? In a p-type material or a p-type semiconductor, there is an increase in density of unfilled states. ये unfilled states क्या, ये हम अगली स्लाइड पे करेंगे. And in p-type material, thus more electrons can be accommodated at lower energy states. At room temperature, the number of holes in the valence band is greater than the number of electrons in the conduction band. The number of holes in the valence band, यहाँ पे holes ज़्यादा हैं, valence band में holes ज़्यादा हैं, then the number of electrons in the conduction band. Conduction band में कम electrons हैं और ज़्यादा holes हैं. Hence, the probability of occupation of energy level by holes in the valence band is greater than the probability of occupation of energy level by electron in the conduction band. Valence band में क्योंकि vacancies ज़्यादा पड़ी, therefore the probability, chances of occupation of energy level, जो vacancy की occupation है in the valence band is greater, ज़्यादा chances हैं कि valence band में जो holes पड़े हुए हैं वो पहले occupy हो जाएं, उसकी ज़्यादा probability है, उसकी ज़्यादा chances हैं. ठीक है. This probability of occupation of energy level is represented in terms of Fermi level. तो लिहाजा आपका जो Fermi level है वो नीचे fall कर जाता है. It becomes smaller. Therefore, the Fermi level in p-type material lies very close to the valence band. The Fermi level of p-type semiconductor is given by this formula. उसकी ये definition. तो अब ये जरा बात गौर से सुन लें कि what is meant by probability and what is meant by occupation of energy level. Probability तो हो गया कि what are the chances of such and such act, और occupation of energy level कि जो आपके वैलेंस शेल में या आपके कंडक्शन शेल में या वैलेंस बैंड में या कंडक्शन बैंड में जो वैकेंसी पड़ी हुई है उसको फुल करने के प्रोसेस को करते हैं ऑक्यूपेशन. ऑक्यूपाई कर लिया आपने, वो ऑक्यूपाई कर लिया आपने, वो रिजर्व कर लिया या आपने उसको कंज्यूम कर डाला. दिस इज ऑक्यूपेशन. ऑक्यूपेशन, और ये ऑक्यूपाई से निकला है. ऑक्यूपाई का क्या मतलब है? ऑक्यूपाई को उर्दू में क्या बोलेंगे?
जगह अडॉप्ट कर लेना.
जी,
और कोई जगह हो उसको अडॉप्ट कर लेना.
सो कोई इफ देयर इज अ वैकेंसी आप उसको अडॉप्ट कर लेते हैं, आप उसको कंज्यूम कर लेते हैं, आप उस स्पेस को यूज करना शुरू कर देते हैं. दैट इज ऑक्यूपेशन. एंड व्हाट इज ऑक्यूपेशन ऑफ एनर्जी लेवल्स? कि जो वैलेंस बैंड में या जो कंडक्शन बैंड में वैकेंसीज थी उनको आपने ऑक्यूपाई कर लिया. दैट इज ऑक्यूपेशन ऑफ एनर्जी लेवल्स. सो दोबारा से कर लेते हैं, इसको हम दोबारा से करने लगे हैं. कि in p-type semiconductor there is an increase in density of states. Thus, more electrons can be accommodated at low energy states. Low energy states का क्या मतलब है? लो एनर्जी स्टेट कौन सी है? कंडक्शन बैंड या वैलेंस बैंड? वैलेंस बैंड. सो यहाँ पर लोअर एनर्जी स्टेट से मुराद है वैलेंस बैंड. अच्छा, आगे एक्सप्लेनेशन ये है कि एट रूम टेम्परेचर द नंबर ऑफ होल्स इन द वैलेंस बैंड इज ग्रेटर देन नंबर ऑफ इलेक्ट्रॉन इन द कंडक्शन बैंड. के दैट इज फॉर इन पी टाइप मटेरियल the number of holes in the valence band is greater than the number of electrons in the conduction band. Hence, the probability of occupation of energy levels by holes in the valence band. Chances कि आपके chances क्या हैं फिर कि valence के occupation of energy level by holes in the valence band is greater than the probability of occupation of energy levels by electron in the conduction band. उसकी ज़्यादा है. This probability of occupation of energy level is represented in terms of Fermi level. इस probability को आप शो कैसे करते हैं? आप शो करते हैं इसलिए लाइन लगाकर, ये लाइन लगाकर which shows the Fermi level. This line shows the Fermi level, which represents that वैलेंस बैंड की तरफ ज़्यादा प्रोबेबिलिटी है कि होल्स को ऑक्यूपाई किया जाएगा और कंडक्शन बैंड की जानब थोड़ी प्रोबेबिलिटी है कि इलेक्ट्रॉन्स यहाँ पे आएंगे. दिस इज द कॉन्सेप्ट ऑफ फर्मी लेवल. So it represents the greater number of chances of occupation of holes or occupation of electrons. P-type material में Fermi level valence band की जानब ज़्यादा होता है और N-type material में Fermi level या chance of occupation conduction band की तरफ ज़्यादा होता है. N-type मटेरियल में ज़्यादा चांस है कि इलेक्ट्रॉन्स आ जाएंगे कंडक्शन बैंड में. P-टाइप में ज़्यादा चांसेस हैं कि आपके जो होल्स हैं वो ऑक्यूपाई हो जाएंगे. और दिस इज रिप्रेजेंटेड बाय द फर्मी लेवल एंड गिवन बाय फार्मूला ओवर हियर. यहाँ पे ये फार्मूला दिया गया, ये फार्मूला दिया गया. So, summarize just as a summary जो अब तक हमने काम किया कि in p-type material there is an increase in density of unfilled states, thus electron can be accommodated at lower energy levels. ये p-type material है, ये आपका Fermi level है. यहाँ पे ज़्यादा इलेक्ट्रॉन्स, यहाँ पे ज़्यादा होल्स अवेलेबल हैं और इलेक्ट्रॉन इधर आ सकते हैं. Whereas in n-type semiconductor density of state is increased, thus electron can be accommodated in higher energy levels. Higher energy level का मतलब ये है कि n-type material में conduction band की तरफ ज़्यादा large possibility कि electron will be available in the electron will be replaced in the conduction band. अच्छा, आप ज़रा गौर से सुन लें. In intrinsic materials, in intrinsic semiconductor, the number of electrons in the conduction band and the number of holes in the valence band are not equal. Hence, the probability of occupation of energy level in conduction band and valence band are not also equal, क्योंकि तादाद ही different है. Therefore, the Fermi level for extrinsic semiconductor lies close to conduction band or valence band. ये डायग्राम को जरा गौर से देख लें कि we have three type of material. First we have intrinsic material जिसमें डोपिंग नहीं की हुई, तो उस केस में आपका जो फर्मी लेवल है that is in the middle. देन वी हैव एन टाइप सेमीकंडक्टर। तो ज़्यादा चांसेस हैं, ज़्यादा प्रोबेबिलिटी है कि आपके कंडक्शन बैंड में इलेक्ट्रॉन्स आ जाएंगे। तो फर्मी लेवल इज नाउ क्लोज टू द कंडक्शन बैंड। और पी टाइप मटेरियल में जहाँ पे होल्स की ज़्यादा तादाद है, जहाँ पे होल्स मेजॉरिटी में है, वहाँ पर फर्मी लेवल आपके वैलेंस शेल के ज़्यादा करीब आ जाएगा, which shows that there is large probability of fulfillment of holes in the valence shell. तो in other words ये फर्मी लेवल हमें क्या बताता है? फर्मी लेवल is also defined as work done to add an electron to the system. More positive यानी more holes in p-type semiconductor, meaning less work done. Less meaning lesser work needs to be done, hence a lower Fermi level. So n-type material में we need large amount of energy, and in p-type material we need very small amount of energy to allow electron to fill in the valence shell. और n-type में we need large amount of energy so that this energy can be given to the electron, जो के बाद में कहाँ चले जाएगा? It will go in the conduction band. So as an example, we see the energy diagram for n type and p type. और ये n type के लिए यहाँ पे we just need this amount of energy to make electron flow into the conduction band. और p type में ये एनर्जी बहुत कम होगी, बिकॉज p type में आपने इलेक्ट्रॉन को फुलफिल करवाना है इन द एक्सेप्टर एटम, और उसके लिए एनर्जी बहुत कम चाहिए. Now we have two concluding slides. ये concluding slides हैं. Fermi function gives the probability of a given available electron energy state to be will be occupied at a given temperature by this formula. और इसके आगे definition, और फिर आगे density of state. The Fermi function gives the probability of occupying an available energy state, but this must be factored by number of available energy state to determine how many electrons would reach the conduction band. This density of state is the electron density state, but there are differences in its application for conductor and semiconductor. For the conductor, the density of state can be considered to start at the bottom of valence shell and fill up to the Fermi level. But since conduction band and valence band overlap, the Fermi level is in the conduction band. So there are plenty of electron available for conduction. और फिर इसके आगे ये इसके formulas हैं which describe the density of states. तो अच्छा, आपकी क्लास का टाइम तो नहीं खत्म हो रहा?
सर अभी 20 मिनट्स में.
नो सर.
ये जो फर्मी फंक्शन है, this Fermi function gives the probability chance, the probability number that a given available electron will be occupied at a given temperature. These functions come from Fermi statistic and has a form of the formula is this, where the basic nature of function dictates that at ordinary temperature most of level up to Fermi level EF are filled and relatively few electrons have energy above the Fermi level. The Fermi level is on the order of electron volt. For example, 7 electron volt for copper, whereas the thermal energy KT is only about 0.026 electron volt at 300 Kelvin. If you put those numbers into Fermi function at ordinary temperature, you will find that value is essentially 1 up to the Fermi level and rapidly approaches 0 above it. तो ये जो 1 है, इसका क्या मतलब है? इसका मतलब ये है कि उसका ज्यादा चांसेस है वो फर्मी लेवल तक ही रहेगा, और फर्मी लेवल से ऑनवर्ड्स अगर आप चलेंगे तो फिर उसकी जो अप्रोच है वो जीरो से अबव हो जाएगी. अप्रोच इज 0 अबव इट, वो 0 को अप्रोच करना शुरू कर देगी. तो ठीक है, बस करें यहाँ तक.
यस सर, काफी सर.
चलें ठीक है. तो जरा दोनों सिया जरा मुझे राब्ता कर लें जरा.
एक्सक्यूज मी सर.
हाँ जी जी
सर
पूछे.
ये लेक्चर्स कहाँ अपलोड होंगे?
ये लेक्चर इसके मेरी बात सुने, लेक्चर्स जो है मैं रिकॉर्ड कर रहा हूँ और आप ये इसी फाइल में डाउनलोड कर लें.
सर ये हम नहीं असेस कर सकते, अगर आप डाउनलोड करके दोबारा अपलोड करें फाइल सेक्शन में तब असेस होगा.
अच्छा अच्छा, यानी मैं पहले डाउनलोड करके अवेलेबल कर दूं?
जी सर.
यस सर.
ओके ठीक है, मैं कर दूंगा.
थैंक यू सर.
मैं इंशाल्लाह.
थैंक यू सर.
तो अभी जरा सब सुन ले कि अभी हमारा ये चैप्टर कंप्लीट नहीं हुआ. अभी हमने नेक्स्ट लेक्चर्स में एक दो और लेक्चर्स में इस चैप्टर को कंप्लीट करना है. ठीक है, तो ये जो हाँ बस ठीक है, ये हमने कंप्लीट करना है. ओके, थैंक यू वेरी मच.
सर देयर इज अ क्वेश्चन.
जी पूछें.
सर अगर फर्ज करें कि फर्मी लेवल अभी हमने अचीव नहीं, तो हमारे पास कुछ इलेक्ट्रॉन जो होंगे वैलेंस शेल में, और फर्ज करें कुछ इलेक्ट्रॉन है कंडक्शन बैंड में, और अगर कंडक्शन बैंड में कुछ इलेक्ट्रॉन्स हैं, बाद में हमने फर्मी लेवल अचीव किया यानी 0 केल्विन पर लेके आए हैं, तो बाद में अगर इलेक्ट्रिक फील्ड अप्लाई करेंगे तो उस कंडक्शन बैंड में इलेक्ट्रॉन्स हैं उन पर इलेक्ट्रिक फील्ड का असर होगा या फिर उन पर भी असर नहीं होगा?
द क्वेश्चन इज, देखें 0 केल्विन में तो आपने एनर्जी एक्सट्रैक्ट कर ली, तो मुझे इसके पहले इसका जवाब दें कि 0 केल्विन के ऊपर वो इलेक्ट्रॉन जो आपके कंडक्शन बैंड में बैठा हुआ है, क्या वो वहीं बैठा रहेगा या क्या वो वापस वैलेंस बैंड की तरफ आ जाएगा? पहले इसका मुझे जवाब दें. आपकी अपनी अंडरस्टैंडिंग क्या है इसके बारे में?
सर 0 केल्विन में उसकी एनर्जी हम एक्सट्रैक्ट कर रहे हैं, तो मींस वो नीचे आने की कोशिश तो करेगा.
नहीं, कोशिश आपकी अंडरस्टैंडिंग क्या है कि एक एटम है, उसमें कंडक्शन बैंड में एक इलेक्ट्रॉन पड़ा हुआ है, आपने उसको 0 केल्विन पे रख दिया, तो अब वो इलेक्ट्रॉन जो कंडक्शन बैंड में था क्या वो वहीं रहेगा या क्या वो वापस वैलेंस शेल अपनी एनर्जी लूज करके वापस वैलेंस शेल में आ जाएगा?
लूज करके आएगा वैलेंस शेल में।
तो ठीक है, इसका मतलब है कि 0 केल्विन में तमाम इलेक्ट्रॉन्स वापस वैलेंस शेल में आ जाते हैं। ये अंडरस्टूड होगी बात?
यस सर।
ठीक है, अब ये बताएं कि अब अगर आप 0 केल्विन में, क्योंकि तमाम इलेक्ट्रॉन्स वापस वैलेंस शेल में बैठे हैं, अगर आप एक्सटर्नल फील्ड लगाते हैं तो क्या वो ज्यादा अपने न्यूक्लियस की तरफ जाएंगे कि बाहर किसी एक्सटर्नल फील्ड की तरफ चले जाएंगे?
और वो तो वही रहेंगे, उन पर असर नहीं होगा इलेक्ट्रिक फील्ड का।
तो ये आपकी आंसर मिल गया ना फिर आपको?
यस सर।
ठीक है। अच्छा, तो जो आपके दोनों क्लासेस के सीआर हैं वो मुझे टेलीफोन पे रब्ता करें जरा 15 मिनट बाद, और दोनों सीआर क्लास की अटेंडेंस मुझे प्रोवाइड कर दें। ओके, थैंक यू वेरी मच। ये मेरा पैगाम दोनों सीआर
एंड
को
सर
पहुंचा दें।
अगर
Sir, kindly share the
और
slides.
सर अगर
हाँ, मैं स्लाइड शेयर करूंगा क्योंकि अभी वो डाउनलोड करके मैं फिर अपलोड करूंगा।
और सर अगर फर्मी लेवल और इलेक्ट्रिक फील्ड को साइमल्टेनियसली अप्लाई किया जाए तो फिर क्या होगा?
मुझे आपका सवाल समझ नहीं आया।
सर अगर फर्मी लेवल और